Today's lesson is called Introduction to Linear Functions. So we're starting the new chapter. We have worked with two variable linear equations and their graphs, such as y equals 2x plus 8. We can also look at these linear equations as linear functions. Remember what a function is? Each input has one output. Let's review what makes a function linear. So in this chart, you're going to see equation, graph, and table, and then we'll do a quick little summary. So when it comes to equations, you can see an example of a function on the left, f of x equals 2/3 x plus 4. What makes this one linear is that you have an exponent here that is a 1 on the x. If you don't see anything there, that's what's really there. When you look at the equation on the non-example side, so you've got f of x equals x squared minus 4x. Yes, the x next to the -4 would have an exponent of 1, but the problem is right here, we have an exponent that is not a 1. And that's the best way to explain it. Don't get into what the exponent is. Just say if it is a 1, that means it's linear. If it's not a 1, that means it's nonlinear. In the example underneath, you can see it's not an example of a linear equation again because of the issue with this having a variable in the exponent position. When you're looking at a graph, you can see linear on the left as an example. We have a straight line. So if I were to find the rate of change on this graph, identify a couple of points and count the rise over the run. It would be consistent. When we look at the graph on the right, you can tell that it's not a linear function because of the curved shape. We're definitely not going to have a constant rate of change here. The slope between the points is not going to be the same. It's going to depend on what interval you're finding. For the table, when we look at that quickly, if I take a look at the table on the example side, if I start to look at my change in my y over my change in my x, I can see that this first row to the second row, I went up 4, while the x's went up 1. From 3 to 7 went up 4. From 1 to 2 went up 1. From 7 to 11 went up 4. 2 to 3 went up 1. So if I were to actually find this slope or change in y over change in x, I'm getting 4 over 1 or 4 every single time. When I take a look at the table on the non-example side, if I try to look for this plus or minus pattern, I see here we added 1/2 while we added 1. And then here we added 1/2 while we added 1. So far so good. But then I get to adding 1 and adding 1. But then here I'm adding 2 and adding 1. So I went from having a rate of change of 1/2 over 1 or 1/2 to 1 over 1, which is 1, to 2 over 1, which is 2. So I don't have a consistent pattern there. Instead, what's really happening here is that we're timesing by 2. And that's not a linear function. And we'll look more into what those types of functions look like in the future. But right now we're concerned with whether it's linear or it's not. So to summarize, functions can appear in 3 basic formats. So remember, we can have an equation, a graph, and a table. When it comes to the equations, as we said up top, a linear function is going to have an equation whose exponent is 1. When it comes to looking at the graph, we are looking for a linear function to have a graph that is a straight line. And then lastly, if we're looking at a table, linear functions have a table whose rate of change is constant. So this chapter is all about linear functions, and there are certain things that you are expected to be able to do with a linear function. So some of this is going to be review of prior concepts we've talked about, and it's a nice overview of everything that's, again, expected for you to know about a linear function. So we'll start with evaluating. We still have to be able to find function inputs and outputs using function notation. So if I see f of 9, remember that means the input or x value is 9. So to find f of 9, I would replace x with 9, making sure I use parentheses for my substitution. Negative 1/2 times 9 would be negative 4.5 plus 7. And that, if you add those up, is going to be negative 2.5. So that tells me that f of 9 is equal to negative 2.5. That was an example of us having the input and finding the output. Now, something else that we've done and that's expected for linear functions would be finding the rate of change or finding the rate of change over a specific interval. So we're going to do that in part B. So find the rate of change over the interval negative 3 is less than or equal to x is less than or equal to 1. So remember, we're going to think of this as an a value and a b value. We first have to find f of a. In our case, that would be f of negative 3. So that's negative 1/2. Negative 3 is going in x's position. So that gives us 1.5 plus 7, right? 1.5. Negative 1/2 times negative 3 would be 1.5 plus 7, which gives us 8.5. And then we also have to find f of b. So f of 1 equals the negative 1/2. We'll put 1 in x's spot. Negative 1/2 times 1 would be negative 0.5 or negative 1/2 plus 7, which gives us 6.5. So if you recall, for finding the rate of change over an interval, we're going to use that function notation of f of b minus f of a over b minus a. So if we do that, our f of b value, which was f of 1, is 6.5. Our f of a value was 8.5. On the bottom, our b value was a 1. We're going to minus from that our a value, which is a negative 3. So just be careful there. We have the double negatives. So that means we are getting negative 2 over 4, which is equal to negative 1/2. So the rate of change over the interval from negative 3 is less than or equal to x is less than or equal to 1 is negative 1/2. Now, if it's a linear function, you should also be able to graph this. Now, you can do this a couple of different ways. Of course, we found a few coordinates. So one way you could do this is to organize the solutions that you found into a table. We have negative 3 and 8.5. We have 1 and 6.5. And then we also found f of 9. So we have 9 and negative 2.5. So that's one way. But because it's a linear function, that means it has a constant rate of change. We can also just use a slope in the y-intercept. So if we look at the equation, it's in mx plus b form. Your slope is negative 1/2. And your y-intercept is 7, which means you're starting at 0, 7 for a y-intercept. So when I go over to the graph, you always start with your y-intercept. So we're going to plot 0, 7. We're going to count, if my slope's negative 1/2, we're going down and right. So down 1 to the right 2, like so. Or again, like I said, you could just plot the coordinates that you already found as solutions. We are going to connect arrows on both ends and label with f of x equals negative 1/2 x plus 7. So it says underneath this, which we've kind of already identified, what is the slope, but they want us to illustrate it on the graph. So our slope is negative 1/2. If I were to pick 2 points, say here and here. I illustrate by showing that I have to go down 1 and to the right 2. So because I went down 1, that's why it's -1. I went to the right 2, that's why it's +2. And then if we look at E, it says, why is the slope from part D the same as the rate of change from part B? So in part D, we got -1/2 for our slope. And if we actually look back up to where we found the rate of change over the interval -3 is less than or equal to x is less than or equal to 1, we got the same exact answer. And that's because for a linear function, the slope is the same between any 2 points. And we talked about that in the chart on the front. You should have a constant rate of change for a linear function. So it doesn't matter where you pick to decide to find the rate of change or slope, it should always be the same. Next, what is the y-intercept of this line, and illustrate on the graph. So remember, the y-intercept is where it's crossing the y-axis. We'll circle there and label that as 0, 7. That's where it's crossing the y-axis. It also says in part G, what is the domain and range of this function? So also review. Remember, wherever we see arrows, we want to kind of mark with infinity to show that it's going to keep going in that direction. And when I try to think of my hands or Post-its or whatever you want to use to do this, for domain, I want to make my Post-its squeeze in from the right and the left, or my hands from the right and the left. And when I try to do that, the arrows will shoot right through. So there's no restriction there on the domain. And the same thing's going to happen when I try to do the range as well. I'll try to pinch from the bottom and the top, and I'm not going to be able to do that. So for the domain, we have all real numbers, which we can write as -infinity to +infinity. And for the range, we also have all real numbers, because we can go from -infinity to +infinity. And then lastly, is this function increasing or decreasing, and why does it behave this way? So if we take a look at this and we're reading it from left to right, when we hit that line, we're going downhill. As the x values are going up, my y values are coming down. So this function is decreasing. And that's because as the x values increase, the y values decrease. So that's just a nice little intro to this chapter to review with you what a linear function is. Remember, for the equation, the exponent has to be a 1. Linear functions will have a graph that's a straight line, and the rate of change will be constant. And if that function is linear, there are many things that you have to be able to do with it, including evaluate input and outputs, find rate of change, graph, identify the slope and y-intercept, and again, all those key features that we've discussed before with functions. So this concludes your lesson on Introduction to Linear Functions.